Hello everyone, welcome to course study on solid mechanics. As we are in unit number 5, that is principal stresses and strain. So our today's topic of discussion is orientation of principal stresses, shear stresses and its magnitude. So what does it mean, orientation of principal stresses and shear stresses? It means that in today's lecture we are going to discuss the direction of principal plane and the plane of maximum shear stress, because these are the two planes which are going to subject principal stresses and the magnitude of maximum shear stresses. So that we are going to discuss in today's lecture, and again we are going to find out the value of its magnitude, that is principal stresses and the magnitude of maximum shear stress. Okay, so our first concept is location of principal plane. Location of principal plane means we are going to find out the direction of principal plane on which the principal stresses are going to act. Okay, so as discussed in the first video, all of you know that what is principal plane. It is a plane which is subjected with only normal stresses. It may be tensile in nature or compressive in nature, and that will be termed as a principal plane. Principal planes will not be subjected with shear stresses, that is, there will be the zero shear stress or tangential stress on an principal plane. So as discussed in this particular slide, principal plane is nothing but it is a plane which is subjected with only normal stresses or the direct stresses. Those stresses, it may be a tensile in nature or compressive in nature. Okay, but it does not subjected to any shear stress value. So the value of shear stress, it is always zero with the principal plane. Okay, now as in the previous videos we have find out the value of sigma n and sigma t on an oblique plane, and those value we are going to use to find out the value of location of principal plane, magnitude of principal stresses, location of maximum shear stresses and the magnitude of maximum shear stresses. So first of all we will consider this particular term, that is tangential shear stress is equal to 0. Okay, so sigma t is equal to 0. So we have sigma t given by sigma x minus sigma y by 2 sine of 2 theta minus tau cos of 2 theta, which is equal to 0. But remember that while finding out the location of principal plane, we have replaced theta by theta p. So in this particular equation I have considered theta p. Okay, instead of theta it is theta p, and which is equal to 0. So on solving this particular equation, I have this equation sigma x minus sigma y by 2 sine of 2 theta p, which is equal to tau into cos of 2 theta p. Okay, therefore the next equation will be tan of 2 theta p, which is equal to 2 tau upon sigma x minus sigma y. This is the location of principal plane which we have find out by using the concept of sigma t equal to 0. Okay, where theta p is nothing but it's a orientation of principal plane on which principal stresses are going to act. Okay, if you calculate the value of 2 theta p from this equation, we will have tan inverse into 2 tau upon sigma x minus sigma y. That will be the value of 2 theta p. Okay, and whatever the answer we will get, if I divide that answer by 2, then we will get the value of theta p only. Okay, and that will be the orientation of principal plane. Okay, in the next slide we are going to find out the magnitude of principal stresses. Okay, that is magnitude of normal principal stresses. All of you know that the principal plane is given by tan of 2 theta p, which is equal to 2 tau upon sigma x minus sigma y. So what it indicate, this 2 theta p is nothing but it is an angle, and tan is nothing but opposite side upon adjacent side. So from this triangle you can see that this 2 theta p it is an angle. Okay, and this tau is the opposite side and sigma x minus sigma y by 2 is the adjacent side. That concept we have used for this particular triangle. Okay, now in the first lecture we have discussed the concept of principal plane, and in that concept we have mentioned that there are three mutually perpendicular plane which are subjected to direct stress. Mutually perpendicular plane means the difference between the angle theta will be the 90 degree. Okay, so this equation tan of 2 theta p, which is equal to 2 tau upon sigma x minus sigma y, it shows that the value of theta differ by 90 degree, and hence two principal planes are mutually perpendicular to each other. Actually this particular concept we have discussed in the first video also. Okay, so from this particular triangle again we will have cos of 2 theta p, which is equal to sigma x minus sigma y by twice r. Remember that r is nothing but it's a resultant of these two value. Okay, and it is shown over here. Okay, and also we have sine of 2 theta p, which is equal to tau upon r. So both these value we are going to put into the equation of normal stress on an oblique plane. So we have the equation of normal stress on an oblique plane given by sigma n is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos of 2 theta plus tau sine of 2 theta. Okay, if I put the value of cos of 2 theta and sine of 2 theta from this into this equation, I have principal stresses given by sigma 1 sigma 2, which is equal to sigma x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 bracket square plus tau square. So what it indicates, it's a magnitude of principal stresses which are going to act onto the principal plane. Okay, what it indicates, it shows that use a positive sign for a maximum value of sigma 1 and use negative sign for a minimum value of sigma 2. So this particular symbol, plus minus symbol, is very important one, because one of the principal stress has a maximum value, maximum magnitude, and another principal stress, the remaining another principal stress, will have the minimum value. Okay, so in that, by using this formula we are going to differentiate maximum and minimum value. Okay, so this is all about the location of principal plane and the magnitude of principal stresses. In the next slide we are going to discuss the concept of location of maximum shear stress. Okay, again we are going to find out the location where the maximum shear stress is going to act. We have sigma t is equal to sigma x minus sigma y by 2 sine of 2 theta minus tau into cos of 2 theta. Again it is the equation of shear stress on an oblique plane. Okay, what we have to find out from this equation, we have to find out the location of maximum shear stress. So how to find out that location? For that purpose we will require to take the derivative of this particular equation with respect to theta and equate it to 0. We will require to take the derivative of this particular equation with respect to theta and equate it to 0. So after taking the derivative we will have d upon d theta sigma t, which is equal to sigma x minus sigma y cos of 2 theta s plus 2 tau sine of 2 theta s, which is equal to 0. Okay, remember that it has to equate to 0 to find out the maximum value of that particular maximum shear stress. Okay, so after solving this equation I have tan of 2 theta s, which is equal to minus, this is the minus sign, minus sigma x minus sigma y upon 2 tau. Okay, and what it indicates theta s, it is the orientation of the plane of the maximum shear stress. So it indicates that it is a plane on which maximum shear stress is going to act. Okay, so by using this particular equation we are going to find out the value of location of maximum shear stress. Okay, and a note is given over there. This equation gives two values of theta s, which are differ by 90 degree, because those are plane perpendicular to each other. Therefore it will give you the value of two values which are differed by 90 degree. Now in the next slide we are going to express the theta s in term of theta p. Okay, to express theta s in theta p, again we have to consider the two equation which we have already derived, that is tan of 2 theta p is equal to 2 tau upon sigma x minus sigma y, and the second equation is tan of 2 theta s which is equal to minus of sigma x minus sigma y by twice tau. Okay, if you observe these both the equation carefully, we will have tan of 2 theta s equal to minus of 1 upon tan of 2 theta p, that is minus inverse. Okay, and minus 1 upon tan of 2 theta p is nothing but it is minus cot of 2 theta p. Okay, so what it indicates, this 2 theta s, this 2 theta p, those are the angles. Okay, and as we have discussed in the trigonometry, tan of alpha plus minus 90 degree will be equal to minus cot of alpha. Okay, so again this is the angle, this is the angle, for this is the angle and this is the angle, and all those value we are going to use to find out the value of theta s. Okay, therefore what it indicate, 2 theta s, that is this value will be equal to alpha plus minus 90 degree. Okay, again we are going to put the value of alpha because this alpha is equal to 2 theta p. Okay, therefore we will have 2 theta s is equal to 2 theta p plus minus 90 degree. So after solving this particular equation, I have the final answer, theta s is equal to theta p plus minus 45 degree. So this equation shows that it is the plane of maximum shear stress which occur at an angle of 45 degree with the principal plane. Okay, so by using this relation you can express the value of theta s in term of 45 degree plus minus theta p. So in this manner we have find out the value of location of maximum shear stresses. So in the today's lecture, first of all we have determined the location of principal plane. Once we have located the principal plane, we have find out the value of magnitude of principal stresses. After that we have located the maximum shear stress, and now we are going to find out the magnitude of maximum shear stress. So next concept is magnitude of maximum shear stress. So we have from this figure, again go to this particular equation, tan of 2 theta s is equal to minus sigma x minus sigma y by twice tau. Okay, again this is an angle and this tan is nothing but it is opposite side upon adjacent side. So opposite side will be the, from this particular triangle, opposite side will be the minus sigma x minus sigma y by 2 and adjacent side will be the tau. So the resultant will be this only. By using this diagram we are going to find out the magnitude of maximum shear stress. Okay, the same diagram, whatever the diagram we have considered over here, this diagram we are going to consider here. Okay, so from this diagram we have cos of 2 theta s, cos of 2 theta s equal to tau upon r, that is adjacent upon hypotenuse, and sin of 2 theta s is equal to minus sigma x minus sigma y by twice r. Okay, so in this manner we have find out two values, cos and sin, and those value we are going to put into the equation of sigma t. So sigma t equation we have, sigma t is equal to sigma x minus sigma y by 2 sin of 2 theta minus tau into cos of 2 theta. Okay, if I put the value of sin 2 theta and cos of 2 theta from this equation, I have maximum value of shear stress. Remember that this sigma t maximum is nothing but it is the maximum value of shear stress. Okay, and it is given by under root of sigma x minus sigma y by 2 bracket square plus tau square. Okay, this is the maximum value of sigma T maximum, that is maximum shear stress. So in this manner we have expressed sigma T maximum in sigma x, sigma y and tau. Okay, if you have to find out the value of maximum shear stress in term of principal stresses, we have the equation sigma T maximum equal to sigma 1 minus sigma 2 by 2 in term of principal stresses. And remember that we have already find out the magnitude of sigma 1 and sigma 2, and that value we are going to use to find out the value of sigma T maximum. Okay, so this is all about the orientation of principal plane, principal plane, principal stresses, maximum shear stress, plane of maximum shear stress. Okay, in the next lecture we will discuss the numericals based on the principal stresses and strain. We will stop here. Thank you.